we're going to skip a little bit here, but today we're going to talk about Dalton's law of partial pressures. Okay, and it says this basically: if you had a mixture of gases, okay, the total gas pressure is equal to the sum of the partial pressures of each type of gas. So what they mean by this is this: in this classroom right now, we have a lot of different gases going on. We have some nitrogen, which is the most abundant gas in this classroom. Nitrogen is the most abundant gas that we have in our atmosphere. We have some oxygen. We probably have some carbon dioxide as well. And there's probably some other ones as well, like maybe a little bit of helium or whatever kind of thing, and little parts this and that. So carbon dioxide, oxygen, nitrogen are probably some of the most common ones in here. But we have there's other gases as well. But what they're saying is this: look, if I wanted to figure out the total pressure of this room, total pressure, I would figure out the pressure of the oxygen gas, I'd figure out the pressure of the nitrogen gas, and I'd figure out the pressure of the carbon dioxide gas, and I'd add those three together, and that would be the total pressure inside this room. Okay? That's all Dalton's law of partial pressures is. We add up what we call the partial pressures. These are the partial pressures here, and however many more I need to. We add up the partial pressures, and we get the total pressure. Okay? I always joke that had I been around a little bit earlier, I'm only 22 now, but had I been around a little bit earlier, I could have probably came up with this law myself and called it BachekChemistry's law of partial pressures. That would have been awesome, eh? But unfortunately, 22, so too young. Okay? But that's all it's saying. Now, this is important, and I'm going to prove this to you in a bit here. Look, it says the greater, and there's a lot of little things here that are super important that we need to pay attention to. If you want to write some stuff down, by all means do so. But we're going to talk about some relationships here between this stuff. Yep. Yeah. Now, it says here this: the greater the amount. Amount is what? Huh? N, or what's the variable? Or what's the units to go with N? Moles, right? What's another word for moles? How else could I describe that? What's another term that we would use instead of moles? Come on, somebody. Amount. What's another? If I knew how many moles I have, what else do I know? How many?
Molar Mass.
No. How many molecules you have? Yes. So another way to say this is the greater the amount, the greater the number of moles you have, okay? The greater the number of molecules you have, the greater its contribution to the overall pressure. So I want you to think about this for a second because this is important. Look, if I have 2 moles, or let's say even I have 2 molecules of a gas, okay, and I have 1 molecule of a gas, or say you got 2,000 molecules and I got 1,000 here. What's going to happen with 2,000? You're going to have twice the number of collisions, right? If you have twice the collisions, that gives you twice the pressure, yeah? If I have 1,000 molecules, I have half the number of molecules, I should have half the pressure, correct? Okay? That is important for us because pressure comes from not what the gas is. It doesn't matter. It comes from collisions between gases. Okay? Pressure comes from collisions. So if I have 2,000 here and I have 100 kilopascals, if I have 1,000, I should get 50 kilopascals. Okay? Kind of deal. That's what this is basically telling us. The greater amount, the more of a certain gas that you have, the greater it's going to contribute to the overall pressure. In this room right now, okay, I'm going to ballpark this because I actually forget the numbers, but about 78% of this room is nitrogen gas. That's the atmosphere is made up of. 78%. So guess what? In this room, the total pressure was, let's say, 100 kilopascals, just for convenience sake. 78 kilopascals would be nitrogen gas. Okay? Good? Let's say oxygen is, I'm just going to make up a number, but I think it's around 16%. if oxygen was 16%, okay, this room would be 16 kilopascals of oxygen gas. Okay? And then whatever the remaining gas is, would be the rest. Okay? I take those three gases and I would add up to the 100% in this room, or the 100 kPa, basically, in that case. I just picked easy numbers. Okay? But that's what it's saying. You know, if its oxygen is 16% or basically has 16% or whatever, well, that's going to contribute less to the overall pressure than the nitrogen does. Okay? The key here is it's proportional as well, and I'm going to prove that to you today. Okay, watch. We're going to get into the first example here. So that's what they're saying here. That's important to remember. Let's take a look at our first example here. So you have this on your sheet here. So listen, it says the following. So I'm going to go ahead right now, and I'm just going to start labeling some stuff. Okay, some variables. I should probably say volume. That's a mass. This is nitrogen. That's N2. That's a mass. This is a molar mass. That's a temperature. Okay. It says we're gonna not worry about calculate the partial pressure. So I guess we're gonna have to calculate P, and then it says calculate the total pressure. We'll get to that in a second. Okay. But when I go through here and I say, okay, let's see what we have. I have volume, I have masses, I have a temperature, okay, and it says calculate the partial pressure of each gas. Okay. Well, a couple options. Okay, so listen. How do you know which formula to use first of all? Well, the first thing I'd say is this. Okay, I see this word here, partial pressure. When I see partial pressure, I think Dalton's law of partial pressure, which is based on the ideal gas law, which is probably what we're going to use to solve this. However, okay, if you think it's the combined gas law, P1, V1, T1, P2, V2, T2, I'd say this. Okay, that's fine if that's what you think. What are the two pressures you're going to compare? There's no pressures up there. What are the two volumes you're going to compare? I only see one volume. What are the temperatures you're going to compare? I only see one temperature. Okay? So I can't use combined gas law because there's only these variables here, yes? So obviously, it looks like to me, I'm going to need to use a little bit of PV equals nRT. I'm going to do this in a chart. I find this works the best for these questions. I'm going to show you one more thing here right away. Nitrogen gas and carbon dioxide gas. Okay? And I'm going to do P and V and N and R and T. And by the way, I have some masses up there. And if I have the mass, maybe I need to know the molar mass as well. Okay? I'm going to write down all those things, and we're going to talk about that in a second here. Okay? But I'm going to make a little chart for myself. And I would highly encourage you guys, you don't have to make a chart, but you do have to make a list of everything that you know for both of these gases, because that's going to be important for us, trust me, down the road here. Okay? Now, the other thing I'm going to say is this. Look, you might say, well, this is PV equals nRT. We just did those questions, Mr. Bachek. Why would I do it here as well? Well, again, we need to use the ideal gas law. But look, it says a 10-liter tank holds nitrogen gas and carbon dioxide gas. So basically, this container has two or more gases in it. And by Dalton's law of partial pressures, it says, hey, let's figure out this gas pressure. Let's figure out this gas pressure. Let's add the two together and get the total pressure. Yes? Okay? But I see right away that I have two gases that are inside this. So I probably have to do this PV equals nRT twice. Okay? Is basically what it comes down to. Now, let's fill in a few things here. Okay? 50 grams of nitrogen, 50 grams of carbon dioxide. I'm going to put that there, put that there. Okay? R, I know R is 8.314. Guess what? It's 8.314. Now, what about the temperature? What do I do about the temperature? It's what temperature? 20 degrees Celsius. So that's roughly about the temperature of this room. What do you know about the gases in this room? They have the same temperature, don't they? Right? They should. They're in the same room. So the oxygen right now, the nitrogen, in fact, the nitrogen and the carbon dioxide right now in this room have the same temperature. Okay? They have the same, if you put the two gases in the same tank, well then it should be the same temperature, yes? Okay? So 20 degrees Celsius is 293.15, of course, kelvins, and 293.15 kelvins. Okay, so that's good. Now, this is where, like I said, I'm going to ask you a question. What's the volume of these gases? What numbers do I need to put down underneath N2 and CO2? What do you think? And this is where I'd refer you to earlier this unit. Would it be? This is what you should know this. Okay? So this is called, ready? Review. Only you should be doing the review. Yes? So listen. In lesson 2, or I think it was 2, we talked about 5 properties of gases. And one of those properties of gases says this: gases always expand to, what's the rest of that sentence? To the container that they're in. Okay? So, again, I'll ask you this. What should I put down for the volume of those gases? Huh? 10 liters for both. Okay? So, the volume here is going to be 10 liters and 10 liters. Okay? And let me explain that to you real quick here. Okay? I'm just going to pick 2 gases. I'm going to call one X and I'm going to call one Z. If I have 2 gases in a sealed container, you know, and I'm not picking on him, but those are the Z's and those are the X's. Do they take up half and half? No. They expand to fill their container. Why wouldn't they? There's no magical barrier here. They're moving until they hit something, right? So that's not a great representation of what this is going to do. Basically, what's going to happen is I'm going to get X, 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 X. I'm going to get the X's to fill up their container, right? They have to. Why wouldn't they? And the Z's are going to be wherever they are. They're going to fill up their container. Z's. Okay? They expand to fill their container. That's what the gas law said. What we're going to do is we're going to say, okay, well, X's are going to create a certain pressure here. Yeah, they might bump into Z's. Okay? But Z's going to create a certain pressure as well. Okay? Based on the number of these gas molecules. Okay? So, going back to here, again, okay, we're going to put 10 liters for both. Okay? Good? Okay. They expand to fill their container. Now, I'm going to give you a little tip here. We're going to fill in this part here. I'm going to say, okay, molar mass of nitrogen, by the way, is what? 28.02 grams per mole. And that's what? 44.01 grams per mole. Okay? And from these two things, this is kind of all the information I could either figure out from the question without doing any, well, I shouldn't say that. This is all this is kind of maybe a little bit more than the information in the question, but that's kind of what I could figure out. And look, the mass and the molar mass can give me N, yes? Mass and molar mass? Mass and molar mass gives me N. And then I have V, N, R, and T, and I can solve for P, of course. Yes? Yeah?
Wait, actually, yeah. I'm still confused.
And if I'm looking for the pressure of each gas, I get the pressure. Yeah. I know, I'm getting back to you. Don't worry. I heard you. I just ignored you. It's different. Okay. But that's what I'm going to figure out the pressure. I'm going to know N, R, T, and V. Yes? And that's how I'm going to fill that in. So if you kind of look at this whole system here, that's kind of what you're getting used to, right? Mass, molar mass gives me N. Now I have N, R, T, and I can find, V, and I can find P. You're asking where the 10 liters came from? Question.
Oh.
Yeah. Good? Okay. So now, I'm going to probably, when you do these questions, I would say this, though. We're going to focus on this gas, get some answers. We're going to focus on this gas, get some answers. Don't try and kind of go back and forth, okay? Just stick to one. It goes a lot quicker, too, if you do that. Okay, so here we go. Calculator, here we go. Move that over here, maybe. And here we go. So, what do I have? Mass divided by molar mass, 50, divided by 28.02, and I get 1.78 moles. Okay? Now remember, we're not round. That's not my answer, so I'm not rounding that. Okay? Now I'm going to take what? nRT and divided by V, yes? Okay, that's what I did down here, right here. nRT divided by V, that should give me the pressure of the nitrogen gas. So, going back to calculator, N times R times T, no, it's T, 293.15 divided by V, 434.912. Actually, for me, I have to write. I'm gonna do this, and if you don't worry about why, but I'm gonna write down here. Well, here I'm gonna do this. No, I'm gonna write down. Hold on. 434.912. What was the rest of it? 4019. Okay. You don't have to write down the entire number. It's fine. Okay. Now, it says up here, what is the partial pressure of each gas? What's the total pressure? So I'm going to tell you right here, okay? The partial pressure, or the pressure of the nitrogen gas that it exerts, is going to look like this. I write a P with a little N2 there to represent partial pressure of nitrogen gas. In other words, just the pressure of the nitrogen gas is 435 kPa. There's one of my answers, the partial pressure of each gas. In this case, 435 for the nitrogen. Okay? Rounded, significant digits. There's 3 in the question, 3 in my answer. Yes?
So you don't subtract like a non-rounded answer from the other non-rounded answer, right? Like what if you're trying to find the total, like you have to add the gas to get the total pressure.
Yeah, I'm not there yet. Just wait.
Okay.
Okay? So that's 435. Okay? Based on 434.912, yada, yada, yada. So I'm going to round it to 435. Okay? Now, I'm going to go to the other side here. I'm going to do carbon dioxide. So, here we go. Let's see. Again, 50 divided by 44.01. Oops. 01. Okay, there's N. R. T. Divided by 10. Okay? And I get what? 276.897. I'm just going to go ahead and write 276.897 kPa. And again, when I record my answer, I'm going to go down here. I'm just going to say the partial pressure of the carbon dioxide is 277. Okay? Good so far. Yeah. Questions? Okay, good so far. We're not done. And then I'd say the following. Okay, that's the pressure of the nitrogen. That's the pressure of the carbon dioxide. If I want to find the total pressure inside this tank, whatever it is, this 10-liter tank, I would add the two together. When I go to add the two together, though, okay, it's the pressure of the nitrogen plus the pressure of the carbon dioxide gas. And of course, the pressure of the nitrogen is this. Now again, I'm not going to use this, and I'm not going to use this because those two are rounded, yes? Okay? So I have to go back on my calculator. If you can do this on your calculator, great. Okay? Here's my last answer, 276.897, blah, 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 blah. Perfect. So I could go plus. So take that answer there and add to it. And if I could, I would arrow up and grab that other number, yes? I'd find it. I can't do that on my calculator for some reason, okay? And I can't do that actually on my other calculator either. It's just that it's a glitch. Apparently some do it and some don't. But if you can go up and grab that number and hit enter and get it down there, perfect, okay? I can't. So that means I would have to type this number out right here. So for me, I have to do this, 434.9124019. And you should use the unrounded numbers. Now, it does work out in this case, but it doesn't always work out. So just be aware that the total pressure, of course, would be 712. Yes? Rounded, et cetera, et cetera. Does that make sense, everyone? So those two added together, which is 712 kPa. Okay? Good? And that would be, by the way, we call this one P tot, which is P total. Yeah? P total. Okay, good. Questions, anyone? So again, making a list is kind of important, I think, for these questions. It kind of gives you an idea of what's the same and what's different. Now, is there any questions? Yes, no? Okay. I do want to point out this. Okay. Now, oh, I didn't write that down. Shoot. I guess I'm going to have to do that again here. 50 divided by 40. 1.136. Now, here's the important part about Dalton's law of partial pressures, and this is something we need to understand, and this is important. I told you before, the more amount you have, the greater it contributes to the overall pressure. In this classroom, if I had twice the number of nitrogens compared to oxygens, the nitrogen should be twice the pressure than the oxygen. This is true. Look, ignore this part down here, because that's how we got this. But look, the temperature is the same. Yes? R is the same. B is the same in these questions. So what does that leave? If the temperature and R and B are all the same, N is directly proportional to P. N determines how much P you get. Yes? Seriously. Wow. Welcome to grade 4. These two directly depend on each other. The more N you have, the greater the amount, the greater the pressure. The greater the amount, the greater the pressure. Right? And guess what? It's proportional. So what I'm saying to you is, look, I'm gonna use some rounded numbers, so this isn't gonna work out perfectly, but watch this. I'm gonna say this is 435 and I'm gonna use 1.78. Watch this. 435 divided by 1.78. Okay? I get about 244. Okay? Pay attention. Hey. $276 divided by 1.136 is about the same. Yes, actually I should have went to 277, shouldn't I? I should have rounded that up. But basically those numbers are going to be identical if I used unrounded numbers. Yes, because the greater the amount, the greater the pressure. It has to be, because everything else is the same. Okay. Everything else is the same. So keep that in mind for down the road. The more amount you have, the greater the pressure. The less you have, the least the pressure. Okay? All right? Now, we're going to do one more example here. I think it's this one right here somewhere, right there. I'm going to let you guys go ahead and make a chart for this and start filling in some stuff, and then we'll talk about that. Okay, so I'd probably go through and label some stuff. Chlorine gas, don't forget, chlorine gas. Temperature. Pressure here, oops, sorry, P. Calculate the mass of each gas, and I think that's all I have. Okay, so I'd want to start with that there, and again, right away when I look at this question, it says a 12-liter tank has both fluorine and chlorine gas. So it's got both of those things there, okay? Right away, I think, two gases in the same container, Dalton's law of partial pressures, okay? So I'd say, okay, let's write down fluorine, chlorine, and let's do some P and B and N and R and T and mass and molar mass, okay? And again, we are trying to find the mass of each gas. Now, 12-liter tank, I can put that in, 12 liters. Uh-oh. Uh-oh. So, again, we can put volumes in there, okay? What do we got? 17.8 degrees Celsius. Both of these gases have to have the same temperature, of course. So 17.8 is, help me out here, what is that? 290.95. 290.95. R we know is 8.314. 8.314. And that leaves me pressure, amount, mass. Do I know the mass? No. Now, it does say this. It says the total pressure, internal pressure, is 1,500. So if I added these two together, it's 1,500. The pressure of the chlorine gas is 450. Okay, the partial pressure of the chlorine gas is 450. And by default, of course, we know that this has to be what? 1050 here, yes? Because 1050 and 450 gives me 1,500 when I add them together. All right? And, by the way, I could probably figure out the mass, or molar mass as well. This would be 38 grams per mole, and this would be 70.90 grams per mole. Okay? So this is all the things I have. And look what I'm, if I want to find the mass, hopefully we remember that in order to find the mass, that is N times big M. Okay? So I just need to know N and big M. And I don't know N, but I could find it out from PV and RT. I'd have PV, RT, I can find N, right? N would, of course, be right here, PV over RT. So I'm going to type that in the old calculator, find N. Use that with the molar mass to find the mass. Yes? So calculator, let's go over here. Come on. And let me just move this up here a bit. There we go. And we're going to use this. So P times V, 1050, times the volume, 12, divided by 8.314 and 290.95. And I get 5.2021 moles. 5.20 moles. Now I can use these two things to find that. Yes? And if I take the moles times the molar mass, I should get the mass, right? So, taking that number there, times it by 38, and I get 198 grams. 3 significant digits because there's 3 in the question, and that's my final answer there for that. That's the mass of the fluorine gas that we would need to use. 198 grams of fluorine gas to create, in a 12-liter tank, to create 1,050 kilopascals of pressure. Okay? On the other side here, again, I'm going to use the 450 here and a V. So what do I got? 450 and 12 divided by 8.314 and 290.95, and I get 2.23 here. 2.23-ish moles with the molar mass times 70.90, and I get 158 grams, 3 significant digits. Okay, multiplying N by big M. Is that good? Questions, anyone? Yes, no? Okay. Again, I want to point out a few things to you. This is important. I'm not just doing this for fun. Again, You know, if you have the volume and R and T, P and N are the only two things that can change, right? Those are only two variables. Look, there's a relationship. If the molecule is going this fast, this temperature going this fast, in this container, okay, and R is the same, 8.314, okay, then N has to create this much pressure, right? If I have more N, it has to create more pressure. Again, look, if you just kind of did the quick math on this, 1050 divided by 5, okay, is about 200-ish, yes? 200-ish, good? Okay? Roughly. If this is 450, that would have to be about, well, this times 200-ish should give you this, yes? Right? Or if this is divided by 200-ish, this has to be divided by 200-ish. Yeah? They have to match up. Okay? Again, because the more molecules you have, the more pressure that gas is going to exert. Okay? And that's important down the road here. And it is proportional, obviously. Okay? I could do the exact same thing I did with the other one. I could take 450 divided by 2.23, find out that ratio, whatever that number is. It's going to be the same number as this. Okay? 1050 divided by 5.20. Of course, you'd have to use the total unrounded numbers, and I didn't do that. Okay, but they'll be the same. It's the same number. Okay, it has to be. Okay, because that's the only thing that's changing. What I do want to point out here is there is no relationship between the masses and the pressures, or the masses and anything else here. Okay, that is a completely different animal, because now you're bringing into the fact, you're bringing in specifically what type of gas it is. Okay. Let me ask you this question here. We got a few minutes here. I'm not going to give you homework, but or not. I could probably record this. But let's say in this room, we're going to talk about this. In this room, I have 1,000 molecules of oxygen gas. 1,000. That's all. Just 1,000. Probably a lot more in real life, but whatever. Let's say I got 1,000 molecules. And they create a pressure of, let's say, 10 kPa. 1,000 molecules of oxygen. What if I changed the gas? And I said, oh, my bad. I didn't mean oxygen. I meant I have 1,000 molecules of nitrogen. Okay? What's the pressure of that gas? Sachi? Yeah. Does it matter what the gas is? What does the pressure come from? No? No? Huh? Yeah. Well, yes. There's a number of, even simpler than that though. Where do you get pressures from? Pressure comes from what? Huh? Pressure comes from collisions, yes? So does it matter if you got 1,000 of oxygens or 1,000 of nitrogens or 1,000 of carbon dioxides? You might think, well, carbon dioxide is a bigger molecule. Not really. They're pretty tiny. They're all pretty tiny. And we're going to talk about that. That's coming up. That's lesson 9. But it doesn't matter what the gas is. Actually, that's lesson 8 and 9. It doesn't matter what the gas is. It matters on how many collisions you have. And what does the collision depend on? How fast they're going? What kind of container do you have? Obviously, if we have this container, and we had 1,000 molecules, there's not going to be many collisions. But if we decide to put in my coffee cup, we're going to have a lot more collisions, right? But again, that's what all these variables that's how they're all related. CV equals nRT, right? But again, it doesn't matter what the gas is. It matters on the amount of the gas, or the number of molecules, or the number of collisions you have. Okay? So that's the